Okay, hi everybody. I'm just gonna keep going through this CPU book thing that I've been reading through. See how far I can get today. It's not super big, but I don't know. We'll see. This is where I left off, just to remind myself. Where were we? By the way, if my voice sounds funny or something today, when I was gone, I got an ear infection, I think, and so I'm not totally. I'm fine now, but my hearing's not totally normal yet, and so I can't hear myself perfectly. And because of that, I've been told that my voice has been sounding funny, but it should be better now than it was. But okay, there are these questions. If the CPU doesn't know about multiprocessing and just executes, oh yeah. So I think the summary was that like CPUs literally are just things that look from one instruction to the next and just execute them, and all these things like processes and applications and whatnot are just like abstractions over that, if I remember right. Um, the questions are: if the CPU doesn't know about multiprocessing and just executes instructions sequentially, why doesn't it get stuck inside whatever program it's running? How can multiple programs run at once? If a program can directly run on the CPU and the CPU can directly access RAM, why can't code access memory from other processes, or God forbid, the kernel? What's the mechanism that prevents every process from running any instruction and doing anything to your computer? And what's a syscall? um, okay, 2 rings to rule them all. Um, okay, the mode, sometimes called the privilege level or ring a processor is in, controls what it's allowed to do. Modern architectures have at least 2 options: kernel/supervisor mode and user mode. While an architecture might support more than 2 modes, only kernel mode and user mode are commonly used these days. In kernel mode, anything goes. The CPU is allowed to execute any supported instruction and access any memory. In user mode, only a subset of instructions is allowed, I/O and memory access is limited, and many CPU settings are locked. Generally, the kernel and drivers run in kernel mode while applications run in user mode. Okay. Processors start in kernel mode. Before executing a program, the kernel initiates the switch to user mode. In kernel mode, you say, read this protected memory. And it says, here you go, dear, with a smiley face. In user mode, you say, read this protected memory. And it says, no, segfault. An example of how, An example, where was I? An example of how processor modes manifest in a real architecture. On x86-64, which is what I think Humble is going to be, the current privilege level, CPL stands for current privilege level, can be read from a register called CS code segment. An example of how the current privilege level, CPL, can be read from a register called CS. Okay. Specifically, the CPL is contained in the 2 least significant bits of the CS register. Okay. Those 2 bits can store x86-64's 4 possible rings. Ring 0 is kernel mode, and ring 3 is user mode. Rings 1 and 2 are designed for running drivers, but are only used by a handful of older niche operating systems. If the CPL bits are 11, 1, for example, the CPU is running in ring 3, user mode. Got it. What even is a syscall? Programs running in user mode because they can't be trusted with full access. Programs run in user mode because they can't be trusted with full access to the computer. User mode does its job, preventing access to most of the computer, but programs need to be able to access I/O, allocate memory, and interact with the operating system somehow. To do so, software running in user mode has to ask the operating system kernel for help. The OS can then implement its own security protections to prevent programs from doing anything malicious. If you've ever written code that interacts with the OS, you'll probably recognize functions like open, read, fork, and exit. Below a couple of layers of abstraction, these functions all use system calls to ask the OS for help. A system call is a special procedure that lets a program start a transition from user space to kernel space, jumping from the program's code into OS code. User space to kernel space control transfers to user space control transfers are accomplished using a processor feature called software interrupts. During the boot process, the operating system stores a table called an interrupt vector table, IVT. x64 calls this the interrupt descriptor table, in RAM and registers it with the CPU. The IVT maps interrupt numbers to handler code pointers. Interrupt vector table. So on and so forth, such forth. Then userland programs. Then userland programs can use an instruction like int, which tells the processor to look up the given interrupt number in the IVT, to switch to kernel mode, and then jump the instruction pointer to the memory address stored in the IVT. Okay. When this kernel code finishes, it uses an instruction like IRET to tell the CPU to switch back to user mode and return the instruction pointer to where it was when the interrupt was triggered. If you are curious, the interrupt ID used for system calls on Linux is OX80. You can read a list of Linux system calls on Michael Karisk's online man page directory. Wrapper APIs, abstracting away interrupts. Here's what we know so far about system calls. User mode programs can't access I/O or memory directly. They have to ask the OS for help interacting with the outside world. Programs can delegate control to the OS with special machine code instructions like int and IRET. Programs can't directly switch privilege levels. Software interrupts are safe because the processor has been pre-configured by the OS with where in the OS code to jump to. The interrupt vector table can only be configured from kernel mode. Okay. Programs need to pass data to the operating system when triggering a syscall. The OS needs to know which specific system call to execute alongside any data the system itself needs. For example, what file name to open. The mechanism for passing this data varies by operating system and architecture, but it's usually done by placing data in certain registers or in the stack before triggering the interrupt. The variance in how system calls are called across devices means it would be wildly impractical for programmers to implement system calls themselves for every program. This would also mean operating systems couldn't change their interrupt handling for fear of breaking every program that was written to use the old system. Finally, we typically don't write programs in raw assembly anymore. Programmers can't be expected to drop down to assembly anytime they want to read a file or allocate memory. System calls are implemented differently across architectures. So operating systems provide an abstraction layer on top of these interrupts. Reusable, higher-level library functions that wrap the necessary assembly instructions are provided by libc on Unix-like systems and part of a library called ntdll.dll on Windows. Calls to these library functions themselves don't cause switches to kernel mode. They're just standard function calls. Inside the library's assembly code does actually transfer control to the kernel and is a lot more platform dependent than the wrapping library subroutine. When you call exit1 from C running on a Unix-like system, that function is internally running machine code to trigger an interrupt after placing the system calls opcode and arguments in the right register, stack, whatever. Computers are so cool. Yeah. The need for speed. Let's get, not sure how to say this, CISC? CISC? Many CISC architectures like x64 contain instructions designed for system calls, created due to the prevalence of the system call paradigm. Intel and AMD managed not to coordinate very well on x64. It actually has two sets of optimized system call instructions. syscall and sysenter are optimized alternatives to instructions like int OX80. Their corresponding return instructions, sysret and sysexit, are designed to transition quickly back to user space and resume program code. AMD and Intel processors have slightly different compatibility with these instructions. Syscall is generally the best options for 64-bit programs, while sysenter has better support with 32-bit programs. Representative of the style RSC RISC architectures tend not to have such special instructions. Arch64, the RISC architecture Apple Silicon is based on, uses only one interrupt instruction for syscalls and software interrupts alike. I think Mac users are doing fine. We're doing all right. Ooh, that was a lot. Let's do a brief recap. Yes, please. Processors execute instructions in an infinite fetch execute loop and don't have any concept of operating systems or programs. The processor's mode, usually stored in a register, determines what instructions may be executed. The operating system code runs in a kernel mode and switches to user mode to run programs. Okay. To run a binary, the operating system switches to user mode and points the processor to the code's entry point in RAM. Because they only have the privileges of user mode, programs that want to interact with the world need to jump to OS code for help. System calls are a standardized way for programs to switch from user mode to kernel mode and into OS code. Okay. Programs. So I'm assuming that when I write this operating system, I need to write. Oh, look, you can see my editing notes. Haha. Don't look at that. Okay. What was I gonna say? I just had like a revelation. I forgot it. Oh yeah. So when I'm writing this OS code, I'm guessing I need to like expose a way for programs to make these syscalls. Right? Programs typically use these syscalls by calling shared library functions. These wrap machine code for either software interrupts or architecture-specific syscall instructions that transfer control to the OS kernel and switch rings. The kernel does its business and switches back to user mode and returns to the program code. Let's figure out how to answer my first question from earlier. If the CPU doesn't keep track of more than one process and just executes instruction after instruction, why doesn't it get stuck inside whatever program it's running? How can multiple programs run at once? The answer to this, my dear friend, that's me, the dear friend, is also the answer to why Coldplay is so popular. Clocks. Wait, hold on. Well, technically timers. I just wanted to shoehorn that joke in. I haven't listened to enough Coldplay to get the joke. I'm sorry. Slice dat time. Let's go check it out. This one long. It's not too bad. Okay. Slice dat time. Hey, this thing's open source. Give it a star. It's pretty good. Quite good so far. I've learned a lot. Let's say you're building an operating system and you want users to be able to run multiple programs at once. That's exactly what I'm doing, and that's what I want to do. You don't have a fancy multi-core processor though, so your CPU can only run one instruction at a time. Okay. Luckily, you're a very smart OS developer. Thank you. But I'm afraid that that's not a very accurate statement. You figure out that you can fake parallelism by letting processors take turn on the CPU. If you cycle through the processes and run a couple instructions from each one, they can all be responsive without any single process hogging the CPU. But how do you take control back from program code to switch processes? After a bit of research, you discover that most computers come with timer chips. Oh. Who knows what that means? You can program a timer chip to trigger a switch to an OS interrupt handler after a certain amount of time passes. Alright, this is sounding good. This is sounding promising. Hardware interrupts. Earlier we talked about how software interrupts are used to hand control from a user land program to the OS. These are called software interrupts because they're voluntarily triggered by a program. Machine code executed by the processor and the normal fetch execute cycle tells it to switch control to the kernel. You're reading program code 011010010001101, and then bam, interrupt triggers context switch. And then you're reading kernel code 001110100100111. Oops, I messed up. 000101001. Okay. OS schedulers use timer chips like PITs. What's a PIT? It's a programmable interval timer. It's a counter that generates an output signal when it reaches a programmed count. The output signal may trigger an interrupt. To trigger hardware interrupts for multitasking. Before jumping to the program code, the OS sets the timer chip to trigger an interrupt after some period of time. The OS switches to user mode and jumps to the next instruction of the program. When the timer elapses, it triggers a hardware interrupt to switch to kernel mode and jump to OS code. The OS code can now save where the program left off, load a different program, and repeat the process. It's kind of crazy how fast and fluid that all works, and it just feels like everything's running totally simultaneously. This is called preemptive multitasking. The interruption of a process is called preemption. If you're, say, reading this article on a browser and listening to music on the same machine, your very own computer is probably following this exact cycle thousands of times a second. I'm not listening to music right now, but I have like OBS recording over here, and it's doing fine. Time slice calculation. A time slice is the duration an OS scheduler allows a process to run before preempting it. Gotcha. Okay. The simplest way to pick time slices is to give every process the same time slice, perhaps in the 10 millisecond range, and cycle through tasks in order. This is called fixed time slice round robin scheduling. Aside, fun jargon facts. Do you know that time slices are often called quantums? Now you do, and you can impress all your tech friends. I think I deserve heaps of praise for not saying quantum in every other sentence in this article. I already gave you a star. Is that good enough? Speaking of time slice jargon, Linux kernel devs use the jiffy time unit to count fixed frequency timer ticks. Among other things, jiffies are used for measuring the lengths of time slices. Linux's jiffy frequency is typically 1000 Hz, but can be configured when compiling the kernel. Cool. I'm going to start talking about quantums in jiffies. A slight improvement to fixed time slice scheduling is to pick a target latency, the ideal longest time for a process to respond. The target latency is the time it takes for a process to resume execution after being preempted, assuming a reasonable number of processes. This is pretty hard to visualize. Don't worry, a diagram is coming soon. Oh, sweet. Alright. Time slices are calculated by dividing the target latency by the total number of tasks. This is better than fixed time slice scheduling because it eliminates wasteful task switching with fewer processes. With a target latency of 15 milliseconds and 10 processes, each process would get 15 over 10 or 1.5 milliseconds to run. With only 3 processes, each process would get a longer 5 millisecond time slice while still hitting the target latency. Okay. Process switching is computationally expensive because it requires saving the entire state of the current program and restoring a different one. Yeah. Past a certain point, too small a time slice can result in performance problems with processes switching too rapidly. It's common to give the time slice duration a lower bound, minimum granularity. This does mean that the target latency is exceeded when there are enough processes for the minimum granularity to take effect. At the time of writing this article, Linux's scheduler uses a target latency of 6 milliseconds and a minimum granularity of 0.75 milliseconds. Naive dynamic time slice, round robin scheduling. You get process 1 gets 2 milliseconds, and then 3 of them get 6 milliseconds. The target latency is 6 milliseconds. Kernel scheduler goes tick, 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 tick. They all get the same amount of time. Round robin scheduling with this basic timeline calculation is close to what most computers do nowadays. It's still a bit naive. Most operating systems tend to have... Oh wait, I think I misunderstood this. Oh, it's because there's 3... Oh, okay, so the target latency is 6 milliseconds, but there are 3 processes running, 1, 2, and 3, and then it repeats. They each get 1/3 of that. Gotcha. Okay, that makes sense. Round robin scheduling with this basic time slice calculation is close to what computers do nowadays. It's still a bit naive. Most operating systems tend to have more complex schedulers which take process priorities and deadlines into account. Since 07, Linux has used a scheduler called Completely Fair Scheduler. CFS does a bunch of very fancy computer science things to prioritize tasks and divvy up CPU time. Every time the OS preempts a process, it needs to load the new program's saved execution context, including its memory environment. This is accomplished by telling the CPU to use a different page table, then mapping from virtual to physical addresses. This is also the system that prevents programs from accessing each other's memory. We'll go down this rabbit hole in chapters 5 and 6 of this article. Ooh, is this what paging is? Because I always hear people talking about paging, and I never know what it is. Okay, note number 1, kernel preemptibility. So far, we've only talked about the preemption and scheduling of userland processes. Kernel code might make programs feel laggy if it took too long handling a syscall or executing driver code. Modern kernels, including Linux, are preemptive kernels. This means they're programmed in a way that allows kernel code itself to be interrupted and scheduled just like userland processes. This isn't very important to know unless you're writing a kernel or something. I am. But basically every article article. Every article I've read has mentioned it, so I thought I would too. Extra knowledge is rarely a bad thing. Note 2, a history lesson. Oh, perfect. Ancient operating systems, including classic Mac OS and versions of Windows long before NT. What's NT? NT. I don't know. Use the processor to use a predecessor to preemptive multitasking. Rather than the OS deciding when to preempt programs, the programs themselves would choose to yield to the OS. They would trigger a software interrupt and say, hey, you can let another program run. These explicit yields were the only way for the OS to regain control and switch to the next scheduling process. This is called cooperative multitasking and has a couple major flaws. Malicious or just poorly designed programs can easily freeze the entire operating system. And it's nigh impossible to ensure temporal consistency for real-time or time-sensitive tasks. For these reasons, the tech world switched to preemptive multitasking a long time ago and never looked back. Chapter 3, how to run a program. This one's a little bit longer. It's not too bad. Oh, look, it's got code in it. C. Oh, did I mention I'm going to learn C? A bunch of people on the Discord told me I should learn C, and so pretty much just do what they tell me to. So I'm going to learn C. I'm kind of looking forward to it. I don't know exactly how I'm going to learn it yet. I've got a book, but there's a bunch of other resources and there's videos, and of course there's everything under the sun for how to learn C. But I thought I would maybe try to write something in it first, because that's usually how I learn best. I think most people do. Where was I? Okay, how to run a program. So far, my bad. So far, we've covered how CPUs execute. So far, we've covered how CPUs execute machine code loaded from executables, what ring-based security is, and how syscalls work. In this section, we'll dive deep into the Linux kernel to figure out how programs are loaded and run in the first place. We're specifically going to look at Linux on x64. Why? Linux is a fully featured production operating system for desktop, mobile, and server use cases. Linux is open source, so it's super easy to research, and just by reading its source code. I'll be directly referencing some kernel code in this article. x86-64 is the architecture that most modern desktop computers use and the target architecture of a lot of code. The subset of behavior I mentioned, that is x64 specific, will generalize well. Perfect. Most of what we learn will generalize well to other operating systems and architectures, even if they differ in various specific ways. Basic behavior of exec syscalls. You're in user space. You say run this file. It calls this thing on it, which then makes a syscall instruction that jumps over to kernel space and loads and sets up a binary. Tries the bin format. If it's not supported, try it again, I guess. If it is supported, start a new process. Replace the current one. Let's start with a very important system call execve. I wonder how this is said, how it's pronounced. How is the syscall execve pronounced? Execve, execve, execute, exec, execute, exec, 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 execve, execve. Okay. It loads a program and, if successful, replaces the current process with that program. A couple other syscalls, execlp, execvpe, etc., exist, but they all layer on top of execve in various factions. Aside, execvete. Execve is actually built on top of execveat, a more general syscall that runs the program with some configuration options. For simplicity, we'll mostly talk about execve. The only difference is that it provides some defaults to execvete. Curious what VE stands for? The V means one parameter is the vector list of arguments, argv, and the E means another parameter that is the vector of environment variables, env. Various other exec syscalls have different suffixes to designate different call signatures. The AT in execveat is just AT because it is just at, because it specifies the location around execveat. So xvat is the fundamental thing. Xv just, I guess, provides a default for at. The call signature of execve is this. Turns an int. Takes a char star file name, which is like a string, no? I know that much, see at least. Char star const argv, these are like, oh, it's an array. Man, C's type syntax is pretty bad. And then take some arguments and some environment things. The file name argument specifies a path to the program to run. Argv is a null terminated, meaning the last item is a null pointer. List of arguments to the program. The argc argument you'll commonly see passed to C main functions is actually calculated later by the syscall, thus the null termination. The env argument contains another null terminated list of environment variables used as context for the application. They're conventionally key equals value pairs. Conventionally. I love computers. What? Fun fact. You know that convention where a program's first argument is the name of the program? No. That's purely a convention. It isn't actually set by the execve syscall itself. The first argument will be whatever is passed to execve as the first item in the argv count. Wait, where was I? First argument in the argv argument, even though it has nothing to do with the program name. Interestingly, execve does have some code that assumes argv0 is the program name. More on this later when we talk about interpreting scripting languages. Step 0, definition. We already know how syscalls work, but we've never seen a real-world code example. Let's look at the Linux kernel's source code to see how execve is defined under the hood. Syscall define 3 execve const char underscore underscore user underscore underscore user star file name rv and np but user file name user rv user np return do execve get name file name argv np. I definitely don't understand what's going on here, at least not very well. Seeing that this starts on line 2105 of some giant file. What is this actually? Yeah, it's right here. Oh, so this is the Linux source code. Huh. That's interesting. Okay. I was curious why the arity, I don't know what arity is hard-coded in the macro name. I googled around and learned that this was a workaround to fix some security vulnerability. The file name argument is passed to a getName function, which copies the string from a user space to kernel space and does some usage tracking things. It returns a file name structure, which is defined in include linuxfs.h. It stores a pointer to the original string in user space, as well as a new pointer to the value copied in kernel space. File name as a name and a upter, a u pointer. Oh, userland pointer. Okay. Ref cnt, a name, and I name. Not sure what these are. Audit names. The execve system call then do a do execve function. This in turn calls do execve common, viat common with some defaults. The execve call, which I mentioned earlier, also does do execve common, but passes through more user provided options. In below snippet, I've included the definitions of both do execve and do execviat. Okay. What's this? An exviat, a file descriptor, a type of ID that points to some resources passed to the syscall and then to do execviat common. This specifies the, oops, I just totally lost my place. Sorry. Okay, this specifies the directory to execute the program relative to. In execve, a special value is used for the file descriptor argument at fdcwt. This is a shared constant in the Linux kernel that tells functions to interpret path names as relative to the current working directory. Functions that accept file descriptors usually include a manual check, like if fd is at fdcwt special code path. Okay. Step 1, setup. Now that we've reached this, the core function handling program execution. Sorry, we've now reached this, the core function handling program execution. We're going to take a brief step back from staring at code to get a bigger picture view of what this function does. The first major job of this is setting up a struct called Linux bin prm. I won't include a copy of the whole struct definition, but it's linked to. But there are several important fields to go over. This is it. Data structures like mmstruct and mvm area struct are defined to prepare virtual memory management for the new program. argc and envc are calculated and stored to be passed to the program. File name and interp are store the file name of the program and its interpreter, respectively. These start out equal to each other, but can change in some cases. One such case is when running interpreted scripts with a shebang. When executing a Python program, for example, file name points to the source, but the interp is the path of the Python interpreter. Gotcha. That's interesting. Buff is an array filled with the first 256 bytes of the file to be executed. It's used to detect the format of the file and load script shebangs. Bin PRM stands for binary program. There's 2 R's. Let's take a closer look at this buffer, buff. Char buff bin PRM buff size, okay? As we can see, its length is defined as the constant bin PRM buff size. By searching the code base for the string, we can find a definition for this in here. 256. So the kernel loads the opening 256 bytes of the executed file into this memory buffer. Aside, what's a UAPI? You may notice the above code's path contains UAPI. Why isn't the length defined in the same file as the Linux bin PRM? Struct include, this UAPI stands for user space API. In this case, it means someone decided that the length of the buffer should be part of the kernel's public API. In theory, everything UAPI is exposed to user land, and everything non-UAPI is private to kernel code. Kernel and user space code originally coexisted in one jumbled mass. In 2012, UAPI code was refactored into a separate directory as an attempt to improve maintainability. The kernel's next major job is iterating through a bunch of bin format, binary format handlers. These handlers are defined in files like this and this. Kernel modules can also add their own bin format handlers to the pool. Each handler exposes a load binary function, which takes a Linux bin PRM struct and checks if the handler understands the program's format. This often involves looking for magic numbers in the buffer, attempting to decode the start of the program also from the buffer, and or checking the file extension. If the handler does support the format, it prepares the code for execution and returns success code. Otherwise, it quits early and returns an error code. The kernel tries the load binary function for each bin format until it reaches one that succeeds. Sometimes these will run recursively. For example, if a script has an interpreter specified and that interpreter is itself a script, the hierarchy might be bin format script, bin format script, bin format elf, where elf is the executable format at the end of the chain. Format highlight. Scripts. Of the many formats Linux supports, bin format scripts is the first I want to specifically talk about. Have you ever read or written a shebang? I have. At the line at the top of some scripts that specifies the path to the interpreter. I always just assumed that these were handled by the shell, but no, shebangs are actually a feature of the kernel, and scripts are executed with the same syscalls as every other program. Computers are so cool. You keep saying this. Take a look at how this checks if a file starts with a shebang. Whoa. That is interesting. If the file does start with a shebang, the bin format handler then reads the interpreter path and any space-separated arguments after the path. It stops when it hits either a new line or the end of the buffer. There are two interesting wonky things going on here. First of all, remember that buffer in Linux bin PRM that was filled with the first 256 bytes of the file? I do remember. That's used for the executable format detection, but the same buffer is also what shebangs are read in and out of in bin format script. During my research, I read an article that described the buffer as 128 bytes long. At some point after that article was published, the length was doubled to 256 bytes. Curious why, I checked the git blame, a log of everybody who edited a certain line of code, for the line where bin PRM buff size is defined in the Linux source code. Lo and behold, 4 years ago. More than 4 years ago. Huh. Large enterprise clients often run applications out of networked file systems where the IT-mandated layout of project files can end up leading to paths that are longer than 128 characters. Bumping this up to the next order of 2 solves this problem in all but the most egregious cases, while still fitting into a 512 byte slab. Bit slab, right? I don't know. No, byte. Cool. Computers are so cool. Since shebangs are handled by the kernel and pull from buff instead of loading the whole file, they're always truncated to the length of buff. Apparently, 4 years ago, someone got annoyed by the kernel truncating their 128 character path, and their solution was to double the truncating point by doubling the buffer size. Today, on your very own Linux machine, I don't have one. If you have a shebang line more than 256 characters long, everything past 256 characters will be completely lost. Huh. That's interesting. Imagine having a bug because of this. Imagine trying to figure out the root cause of what's breaking your code. Imagine how it would feel discovering that the problem is deep within the Linux kernel. Woe to the next IT person at a massive enterprise who discovers that part of a path has mysteriously gone missing. That does sound like a nightmare. The second wonky thing. Remember how it's only convention for argv0 to be the program name, and how the caller can pass any argv they want to an exec call, and it will pass through unmoderated? It just so happens that the bin format script is one of those places that assumes is the program name. It also removes argv0 and then adds the following to the start of argv. Path to the interpreter, arguments to the interpreter, file name of the script. Let's look at an example execve call. You pass it the name, the path name, the file name, argv, and np. Hypothetical script file has the following shebang on its first line. User's bin node, experimental module. The modified argv finally passed to the node interpreter will be this. Okay. After updating argv, the handler finishes preparing the file for the execution by saying linux bin prm.interp to the interpreter path, in this case the node binary. Finally, it returns 0 to indicate success, preparing the program for execution. Format highlight. Miscellaneous interpreters. Another interesting point is bin format misc. It opens up the ability to add some limited formats to userland configuration by mounting a special file system at this place. Programs can perform specially formatted writes to files at this directory to add their own handlers. Each configuration entry specifies how to detect their file format. This can specify either a magic number at a certain offset or a file extension to look for. The path to an interpreter executable. There's no way to specify interpreter arguments, so a wrapper script is needed if those files are desired. Some configuration flags, including one specifying how bin format misc updates argv. The bin format miscellaneous system is often used by Java installations configured to detect class files by their that, magic bytes, and jar files by their execution. On my particular system, a handler is configured that detects Python bytecode by its .pyc extension and passes it to the appropriate handler. This is a pretty cool way to let program installers add support for their own formats without needing to write highly privileged kernel code. In the end, not the song. An exec syscall will always end up in one of two paths. It will eventually reach an executable binary format that it understands, perhaps after several layers of script interpreters, and run that code. At this point, the old code has been replaced. Or it will exhaust all its options and return an error code to the calling program, tail between its legs. If you've ever used a Unix-like system, I think this is a Unix-like system, Mac OS, no? At least that's what we like to say. You might have noticed that shell scripts run from a terminal still execute if they don't have a shebang line or .sh extension. Yes, you can test this out right now if you have a non-Windows terminal. No, I already knew that. Chmod plus x, yeah. So why does a shell script run as a shell script? The kernel's format handlers should have no clear way of detecting shell scripts without any discernible label. Well, it turns out that this behavior isn't part of the kernel. It's actually a common way for your shell to handle a failure case. When you execute a file using a shell and the exec call fails, most shells will retry executing the file as a shell script by executing a shell with the file name as the first argument. Bash will typically use itself as this interpreter, while Zish uses whatever sh is, usually born shell. Huh. This behavior is so common because it's specified in POSIX, an old standard designed to make code portable between Unix systems. See, I had somebody tell me about this in one of my YouTube comments. Portable operating system interface. It's maintained, specified by IEEE Computer Society. Compatibility between us. See, should Humble comply with POSIX? Huh. See, this would be really interesting. That could be really interesting. An old standard designed to make code portable between Unix systems. While POSIX isn't strictly followed by most tools or operating systems, many of its conventions are still shared. If an exec syscall fails due to an error equivalent to that error, the shell shall execute a command equivalent to having a shell invoked with the command name as its first operand, with any remaining arguments passed to the new shell. If the executable file is not a text file, the shell may bypass this command execution. In this case, it shall write an error message and shall return an exit status of 126. I wonder if like Serenity follows POSIX. Who knows? Oh well. Computers are so cool. Alright, becoming an elf lord. Yes. I want to become an elf lord. Alright, this is interesting. We pretty thoroughly understand execve now. I don't feel like I really thoroughly understand it, but I sort of get the high level view. We pretty thoroughly understand it. At the end of most paths, the kernel will reach a final program containing machine code for it to launch. Typically, a setup process is required before actually jumping to the code. For example, different parts of the program have to be loaded in the right places in memory. Each program needs different amounts of memory for different things, so we have standard file formats that specify how to set up a program for execution. While Linux supports many such formats, the most common format by far is ELF. Executable and linkable format. Okay. Now you've heard of ELF on a shelf. Now get ready for ELF on a GNU Linux. Thank you to Nikki Case for the adorable drawing. That is a nice drawing. Is that a penguin? Is that supposed to be a penguin? That's obviously a GNU. Aside, are elves everywhere? When you run an app or command line program on Linux, it's exceedingly likely that's an elf binary. However, on Mac OS, the de facto format is Mako. Mako. I have heard about this. Mako. Mach-O does all the same things as elf, but is structured differently. On Windows, .exe files use the portable executable format, which is again a different format with the same concept. In the Linux kernel, elf binaries are handled by bin format elf handler, which is more complex than many other handlers and contains thousands of lines of code. It is responsible for parsing out certain details from the elf file and using them to load the process into memory and execute it. I ran some command line kung fu to sort bin format handlers by line count. Whoa. And elf, sure enough, is the greatest of them all. And this other guy also says elf, and he's pretty big. File structure. Before looking more deeply at how bin format elf executes elf files, let's take a look at the file format itself. Elf files are typically made up of 4 parts. Structure of an elf. The elf has a head. Basic information about the binary location of these, PHT and SHT. The program header table describes how and where to load the elf file's data into memory. And the section header table, optional map of the data to assist in debugging. Data, all the binaries data. The PHT and SHT point into this section. Every elf file has an elf header. It has the very important job of conveying basic information about the binary, such as what processor it's designed to run on. Elf files can contain machine code for different processor types like ARM and x86. Whether the binary is meant to be run on its own as an executable or whether it's meant to be loaded by other programs as a dynamically linked library. We'll go into details about what dynamic linking is soon. The entry point of the executable. Later sections specify exactly where to load data contained in the elf file into memory. The entry point is a memory address pointing to where the first machine code instruction is in memory after the entire process has been loaded. The elf header is always at the start of the file. It specifies the locations of the program header table and section header, which can be anywhere within the file. Those tables in turn point to data stored elsewhere in the file. Program header table. The program header table is a series of entries containing specific details for how to load and execute the binary at runtime. Each entry has a type field that says what detail it's specifying. For example, pt load means it contains data that should be loaded into memory, but pt note means the segment contains informational text that shouldn't necessarily be loaded anywhere. Here's some common program header types: pt load, pt note, pt dynamic, pt interp. This would be the data to be loaded into memory. This would be free-form text like copyright notices. Okay. Info about dynamic linking, which he said we're going to get to later. Path to the location of an elf interpreter. Each entry specifies information about where its data is in the file and sometimes how to load the data into memory. It points to the position of its data within the elf file. It can specify what virtual memory address that data should be loaded into memory at. This is typically left blank if the segment isn't meant to be loaded into memory. 2 fields specify the length of the data, one for the length of the data in the file and one for the length of the memory region to be created. If the memory region length is longer than the length of the file, the extra memory will be filled with zeros. Okay, this is beneficial for programs that might want a static segment of memory to use at runtime, but these empty segments of memory are typically called BSS segments. Finally, a flags field specifies what operations should be permitted if it's loaded into memory. PFR makes it readable, PFDub makes it writable, and PFX means it's code that should be allowed to execute on the CPU. Sections header table. Sections header table is a series of entries containing information about sections. This section information is like a map charting the data inside the elf file. It makes it easy for programs like debuggers to understand the intended uses of different portions of the data. It's like a map. I'm not quite understanding what this is here. Or what these are. Nor are these like zombie hands coming up out of the ground. But I like the idea. For example, the program header table can specify a large swath of data to be loaded into memory together. That single pt load block might contain both code and global variables. There is no reason those have to be specified separately to run the program. The CPU just starts at the entry point and steps forward, accessing data when and where the program requests it. However, software like a debugger for analyzing the program needs to know how exactly where each area starts and ends. Otherwise, it might try to decode some text that says hello as code, and since that isn't valid code, explode. Hello as code, and since it's not code, it explode. Okay. This information is stored in the section header table. While it's usually included, the section header table is usually optional. The elf files can run perfectly well with the section header table completely removed, and developers who want to hide what their code does will sometimes intentionally strip or mangle the section header table from the elf binaries to make them harder to decode. So elves can operate just fine without their head, is what I got here. Each section has a name, a type, and some flags that specify how it's intended to be used and decoded. Standard names usually start with a dot by convention. The most common sections are .text, machine code to be loaded into memory and executed on the CPU. SHT progbits type with the SHF execve flag mark it as executable, and SHF alloc flag, which means it's located into memory for execution. Don't get confused by the name. It's still just binary machine code, even though it says text. I always found it somewhat strange that it's called .text despite not being readable text. Your quote here is facing the wrong way. See everybody? This is the wrong way. Data. Initialized data hard-coded in the executable to be loaded into memory. For example, a global variable containing some text might be in this section. If you write low-level code, this is the section where the statics go. This also has the type SHT prog bits, which just means the section contains information for the program. Its flags are SHF alloc and SHF write to mark it as writable memory, BSS. I mentioned earlier that it's common to have some allocated memory that starts out zeroed. It would be a waste to include a bunch of empty bytes in the elf file, so as a special segment type called BSS is used. It's helpful to know about BSS segments during debugging. There's also a section header table entry that specifies the length of memory to be allocated. It's of type SHT nobits and is flagged SHF alloc and SHF write. Row data. Got a great ant row. This is like .data, except it's read-only. In a very basic C program that runs printf hello world, the string hello world would be in a row data, while the actual printing code would be in the text section. That's interesting. Is this... I feel like I've seen this. I feel like I've seen this, because if I go to like a some project of mine, let me make this a lot bigger for you. Okay, if I go to some project of mine, oops, and I look down in like where's the oh, it was hidden, the target. Like, for example, where do these go again? Maybe not that. Target debug fan. Yeah, maybe this is it, I guess. But I guess this is all nonsense, but I feel like sometimes there's places in binaries where I can like see text that I wrote. Like, I wonder if I just made like a very simple, here we go. Ready? Let me get out of here. Let me like go in here and say like cargo new test elf test, and open up the elf test. Then I go here and go here. Now it has this like build, right? Cargo build. Now it has elf test, right? If I search in here, so look, that says hello world. Hello, see this? Check it out. Right here, can you see this? It says hello world. I think that's pretty cool. So that must be the row data, great ant rows data. That's interesting. Okay, so back to Arc. Okay, the Schuster tab. This is a fun implementation detail. The names of sections themselves, like .text and .Schuster tab, aren't included directly in the section header table. Instead, each entry contains an offset to a location in the L file that contains its name. This way, each entry in the section header table can be the same size, making them easier to parse. An offset to the name is a fixed size number, whereas including the name in the table would use a variable size string. Yeah, that's interesting. All the name data is stored in its own section called Schuster tab of type SHT stir tab. Data. The program and section header table entries all point to blocks of data within the elf file, whether to load them into memory to specify where program code is or just to name sections. All of these different pieces of data are contained in the data section of the elf files. Program header entry, program header entry, program section header entry. Okay. So they all just like point to. Ooh, look. See, look, the row data is the hello world. A brief explanation of linking. Yes, I've had some linking grief in my past. Back to the bin format elf code. The kernel cares about two types of entries in the program header table. P2 load segments specify where all the program data like text and data sections need to be loaded into memory. The kernel reads these entries from the elf file to load the data into memory so the program can be executed by the CPU. The other type of program header table entry that the kernel cares about is pt_interp, which specifies a dynamic linking runtime. Before we talk about what dynamic linking is, let's talk about linking in general. Programmers tend to build their programs on top of libraries of reusable code. For example, libc, which we talked about earlier. When turning your source code into an executable binary, a program called the linker resolves all these references by finding the library code and copying it into the binary. That's what a linker does. See, I didn't know that. This process is called static linking, which means external code is included directly in that file that's distributed. However, some libraries are super common. You'll find libc is used by basically every program under the sun, since it's a canonical interface for interacting with the OS through syscalls. It would be a terrible use of space to include a separate copy of libc in every single program on your computer. Also, it might be nice if bugs in libraries could be fixed in one place rather than having to wait for each program that uses the library to update it. Dynamic linking is a solution to these problems. If a statically linked program needs a function foo from the library called bar, the program could include a copy of the entirety of foo. However, if it's dynamically linked, it would only include a reference saying I need foo from the library bar. When the program is run, bar is hopefully installed on the computer, and the foo function's machine code can be loaded into the memory on demand. If the computer's installation of the bar library is updated, the new code will be loaded in the next time the program runs without needing any change in the program itself. Static linking. Library functions are copied from the developer's computer into each binary at build time. Foo gets copy pasted. Okay. Dynamic linking. Binary. There's these references. Oh, look. External references. This is cool. I like the diagrams. These are helpful. Dynamic linking in the wild. On Linux, dynamically linkable libraries like bar are typically packaged into files with the .so extension. These SO files are ELF files, just like programs. You may recall that the ELF header includes a field to specify whether the file is an executable or a library. In addition, shared objects have a .dinsim section in the section header table, which contains information on what symbols are exported from the file and can be dynamically linked to. On Windows, libraries like bar are packaged into .dll, dynamic link library files. macOS uses the dylib, dynamically linked library extension. Okay. Just like macOS apps and Windows exe files, these are formatted slightly different from ELF files, but are the same concept and technique. An interesting distinction between the two types of linking is that with static linking, only the portions of the library that are used are included in the executable and thus loaded into memory. With dynamic linking, the entire library is loaded into memory. This might sound less efficient, but it actually allows modern operating systems to save more space by loading a library into memory once and then sharing that code between processes. Only code can be shared as the library needs different state for the different programs, but the savings can still be on the order of tens to hundreds of megabytes of RAM. Execution. Let's hop on back to the kernel running ELF files. If the binary it's executing is dynamically linked, the OS can't just jump to the binary's code right away because there would be missing code. Remember, dynamically linked programs only have references to the library functions they need. To run the binary, the OS needs to figure out what libraries are needed, load them, replace all the name pointers with the actual jump instructions, and then start the actual program code. This is very complex code that interacts deeply with the ELF format, so it's usually a standalone program rather than part of the kernel. ELF files specify the files of the program they want to use, typically something like this, and a pt_interp entry in the program header table. After reading the elf header and scanning through the program header table, the kernel can set up a memory structure for the new program. It starts by loading all PT load segments into memory, populating the program's static data, BSS space, and machine code. If the program is dynamically linked, the kernel will have to execute the elf interpreter, so it loads the interpreter's data, BSS, and code in memory. Okay. Now the kernel needs to set the instruction pointer for the CPU to restore when returning to userland. If the executable is dynamically linked, the kernel sets the instruction pointer to the start of the elf interpreter's code in memory. Otherwise, the kernel sets it to the start of the executable. The kernel is almost ready to return from the syscall. Remember, we're still in execve. Yep. It pushes the argc, argv, and environment variables to the stack for the program to read when it begins. The registers are now cleared. Before handling a syscall, the kernel stores the current value of registers to the stack to be restored when switching back to user space. Before returning to user space, the kernel zeroes this part of the stack. Finally, the syscall is over and the kernel returns to userland. It restores the registers, which are now zeroed, and jumps to the stored instruction pointer. That instruction pointer is now the starting point of the new program, or the elf interpreter, and the current process has been replaced. Oh look, paging. Alright, this one's pretty long. Should I do it today or not? This one's also pretty long. Was that a video? Cows? And there's an epilogue, which is short. Alright, I will stop there and finish these tomorrow, hopefully. Yeah, so tomorrow we'll start with paging.